我觉得我摸到一点点。
This will be recorded. I don't speak to the quality of the audio, but it'll be recorded for those of us who are getting ready for buckyball. So, Lawrence, I think you were the one that asked the question about this table. And I was right in my interpretation, but I hate this table. And I've seen it a couple of years in a row, and every time I'm like, I hate it. Damn it, Lawrence, it's your fault. Let's make some plots. It's your fault. You're so terrified. So, rule number 1. Type 1 error decreases as the number of samples increases. Right? We can understand that very clearly just thinking about a standard normal distribution. The way that we set up our test statistic, our variance is the variance of the system divided by the square root of the number of observations. And so for fixed significance, right, for fixed values of Z alpha, that bad boy is going to squeeze in, and our type 1 error is going to decrease. Our odds of rejecting the null hypothesis when it is true, of falsely rejecting the null hypothesis, will get smaller and smaller. Oh, that's wonderful, and it doesn't project my avatar here. Second main thing, remember alpha and beta, type 1 and type 2 work in relative opposition to one another. So decreasing in type 1 always increases type 2 if you don't increase the number of observations. And so that's very simple. Here is our H0. Here is our alternative hypothesis. They share the same distribution, right? They share the same variance. Define my confidence in my type 1. This is my type 1 error, my probability of rejecting the null hypothesis when it is true. If I want to be more confident and spread those confidence bounds out, I start chewing into my type 2, my alternative hypothesis distribution. And as I become more confident in alpha, as my type 1 error goes down, my type 2 error gets much larger. I fail to reject the null hypothesis when the alternative hypothesis is true. I like pictures. Holding type 1 constant can decrease increasing the number of observations, we can decrease type 2. So if we don't change our significance, we don't change those values, all we do is sample more. The consequence of that is our null and alternative hypothesis distributions sharpen, and our type 2 error goes down. Another version of that, so this is in value and parameter space, so 100 megapascal, 120 megapascal, right? This is in real physical parameter space. It's weird, if we do the standardization and visualize that, what's actually happening is in standard normal space, in Z space, this distribution shifts to the right. Same outcome, it's just a transformation of the system, but it's useful to see that. Lawrence, did I answer your question?
Yeah.
It's all up. Okay. Power of a statistical test. Basically, it's a measure of how likely we are to reject the null hypothesis when the alternative hypothesis is true. It is maybe the stupidest imaginable thing. It is just 1 minus beta. So, for instance, in that previous example, we found that if we assumed the null hypothesis is 50, the alternative hypothesis is 52, n equals 10, we were able to calculate, and we use sigma of course, we were able to calculate beta as 0.26. The power of the test is 73%. It's just 1 minus, right? It's just the inverse, but it's how confident are we that we successfully can reject the null hypothesis? Okay, bring it back. What's going to happen now is we're going to do a couple of things. We're going to set up how to do a hypothesis test. And just the same as we did when we introduced the distributions and we were talking about what distribution do we do when we're looking for the mean, but we know the variance of the population. If we don't know the variance of the population, if we want the variance, we're going to walk through that same process, but now with an eye towards hypothesis testing. So, reminder, we have 2 types of hypothesis tests. One is the two-sided test. Null hypothesis is, hey, it equals a value. Alternative hypothesis is, Or we have one-sided tests where still the null hypothesis is it equals a value, but now it's no, it's bigger than that, or no, it's smaller than that. Okay? Deciding on which those is, someone asked at some point, how do I determine my confidence intervals? Why do I know which Z is blah, blah, blah? That's your job. It's your job to know your system well enough to know what's tolerable, what's not, what your customer will accept, what they won't, what will cause planes to fall out of the sky and what won't, and you define. I'm just an idiot. I can't tell you that. So one of the disadvantages of traditional hypothesis testing is we sample from the population and we have a fixed significance. We say alpha equals 0.05, right? That's our value. What that does not tell you is quantitatively how confident could you have been, or how confident are you that it is not or it is within those bounds. And so what one uses is the so-called p-value. Idea here is, given my samples, given my understanding of the population distribution and variance, what is the most extreme value that I could have gotten, right? What's the highest Z value that my data support? Not, did it cross that threshold, yes or no, but use the sample to define the threshold. So, as an example, our good old two-sided, H0 is mu is 50, H1, our alternative hypothesis is nah, number of samples is 16, our variance of our population is 2.5, and then the question is, we have an observed sample mean. We've taken some samples, 16 samples, and our sample mean is 51.3. Question is, what is the p-value for that? And so, I'm sorry, bro, are the slides not available online?
Oh, they're available, but it's distorted.
Okay, okay. I just want to make sure. Okay, so my goal is, typically speaking, for p-value, you can do one-sided. Typically speaking, you do two-sided. So you say, hey, given that I'm this far away from my mean, let's consider the symmetric version of that. right? 51.3 and 48.7. And my question is, how much of the distribution is below or above that value? And then from that, calculate the z-value. No, I do z-value, then I do the probability, sorry. So 1 minus the probability that I'm integrated between these two is this distribution. I use my normal distribution x statistic, so what's the z-value for that, for 48.7? What's the z-value for 51.3? Calculate this out. That ends up being about 96% of the distribution. And so my p-value is 0.38, or 3.8%, right? You can see that that's quantitatively different. If I had just done a hypothesis test and said, is it more than 5% out? The answer is, of course, yes, right? Sure, because 0.38 is less than 0.5. So hypothesis test succeeds. But that's not actually the power of your sample. That's not telling you quantitatively how far, how unlikely is it that a sample would have these values. That does. Of course, yeah, Lawrence, what's on, bro?
So, smallest level of significance will lead to rejecting null hypothesis. So, does this mean that if a given conclusion has a p-value and the type 1 error is at least that p-value, then the null hypothesis will always be rejected? But isn't there like always possibility that it will
I'm about to talk about that right here.
Oh.
This slide. Spot on. Michelle. Okay, so what we have to remember is that we're always randomly sampling from the population. There is never a 0% probability that you would fail to reject the null hypothesis based off of a sample of more or less any size. So on the right, on your left, this is an example where the null hypothesis is true, right? And this is the power across multiple different trials. Let's practice our statistics vocabulary. What kind of distribution is the one on the left? Uniform distribution. See, you should have spoken up. So, mostly, if we set a significance level of 0.05, mostly we would we would not reject the null hypothesis. However, every now and again, we're going to get a bum sample and we're going to reject it. Similarly, for the case where the null hypothesis is actually false, I mean, yeah, you know, the p-value is slammed up against the left side of that thing, so 80% of the time, 85% of the time, we're going to correctly reject the null hypothesis. But we could get bum samples. Does that address your question that you meant to ask, Lawrence?
Just for the left graph.
Sure.
So why would the possibility that the null hypothesis is rejected be this like approximately the same for like, for example, p-value equal to 0.05, p-value equal to 0.9? Because if p-value is 0.9, that means the smallest level of significance that will lead to rejecting the null hypothesis is 0.9. So Like, I guess my question is, when you say smallest level of significance, what is it being compared to? What is the smallest out of?
Given my observations, so understanding that we're on our standard normal distribution, right? We're there. Given my observations, how unlikely would it be for me to have falsely rejected the null hypothesis? Right? It's just, how unlikely is it? I've got a bunch of samples. I know what my distribution looks like. I have a mean value for those. How does that compare? Where on that distribution is that value? Is it here? Or here? Or is it all the way out in the tails?
So given that you've rejected the null hypothesis, the p-value is how likely was the rejection a result of a type 1 error?
Yeah. Smallest level of significance that would lead to the rejection of a null hypothesis with the given data. And so, how likely is it that I would falsely reject it?
So basically, given that we've rejected the null hypothesis, how likely was that we were wrong?
More or less, yeah.
It's close to 0. Just like an example.
Derek?
In this case, we chose the upper bound to be 51.3, and that's the mean that we measured.
That's the mean that we measured.
And then the
48.7 is
comes
just,
to-
it's a
Symmetric.
it's a symmetric, wonderful. It's a sort of semantic question, right? It's how, given that it's a symmetric distribution, how likely is it that I would have picked as extreme a value on either side? Like, given that I'm starting to get towards the tails of the distribution, how likely is it that I would have just randomly grabbed a sample of 50 points that were way out there? You think to yourself, wow, that's fantastic, that's wonderful, it's the most principal. So remember that there's no right answer. When you're sampling, there's no ground truth. There's an expectation there's a population that is unmeasurable. You're always only sampling. Even if you've been making alloy, that same alloy for 100 years, and that's the average value that you get, it still could be a sampling error. Them's the breaks. What people do, it's still a statistically justifiable method. It's how likely was I to have gotten this random ass answer that disagreed with the null hypothesis. In principle, that's wonderful, right? So everyone should be sampling, calculating that against their null hypothesis, and you should get p-values all over the place in the literature, from 0.7 to 0.07 to 0.0007, based solely on sampling. What you find is common practice, especially in the softer sciences, sociology, medicine, where factors get squishy, is people arbitrarily set a p-value of 0.05 and sample and discard outliers until they're able to show that they've crossed that magical threshold, and then it's time to publish and call CNN. This is called p-hacking. Okay, so the general procedure for setting up a hypothesis test. 7 steps, relatively straightforward. Step 1, what is my parameter of interest? What am I testing against? 2, what is my null hypothesis? 3, state the alternative hypothesis. 3 or 4, and we'll talk about this, is what's my test statistic? Am I checking for variance? Do I know the population mean? Or do I know the population variance? Reject, state what the rejection criteria is for the null hypothesis. Calculate, draw conclusions. Pretty straightforward, right? It's good to be formula. It's one of the few cases in this class where I can honestly say there is a really straightforward way of getting to an answer. Mostly we live in an uncertain world. So how do I know what the appropriate test statistic is? It comes down to what am I trying to measure? And do I know the population variance? If I do know the population variance, because I'm estimating the mean, I live in central limit theory world, I use the normal distribution. And so my test statistic is Z. I normalize or standardize using that formula. My null hypothesis is head, mu is mu0. I have a test statistic, which is how much different is my sample mean from my population mean, or my proposed population mean. And then to calculate null hypothesis, if it's then I'm going to use Z alpha over 2. And I'm looking for the calculation of that Z0 value to be less than that or greater than that. If it is, I reject the null hypothesis. If I'm looking to calculate the probability, right, it's just 2 times 1 minus the cumulative distribution function, which you've done now numerically. If it's no, it's bigger, it's 1 minus that. If it's no, it's less than, it's just that. Just greater than, is that part of the distribution? So I have to calculate this part and then take 1 minus to get that. Less than is just that part of the distribution. And we're off to the races, right? We've contextualized the problem appropriately. We've identified our test statistic. We've decided on what our alternative hypothesis is and how are we going to measure whether or not we reject it. And it's the typical high school plug and chug. Pluggity chuggity. So walking through an example. We're back to propellants. Population says it needs to be 50 centimeters per second. Standard deviation is 2 centimeters per second. We need a significance level of 0.05 because p-hacking. And we took a random sample of 25 samples, 25 measurements. Our parameter of interest is burn rate, mu. Our null hypothesis is what we want it to be. Our alternative hypothesis is Our test statistic is PowerPoint drop in my formulas again. Test statistic is Z, right? It's a normal distribution. We know the variance of our population. We're going to reject it if the p-value is less than 0.05. We can either look at a table, have it memorized in our brains, or otherwise calculate it that Z of 0.025, remember we split, 1.96, and the negative value is negative 1.96. Oh, I dropped the equals. Since we know our sample mean, and we know our variance and our number of samples, we just calculate z0, right? It's a z-value of 3.25. Is that bigger than 1.96? Yeah. And so, we reject the null hypothesis. We can also calculate the p-value, which is 0.012. And we're done. We reject the null hypothesis, and we do it at a fairly high level of, if we want to do a power or p-value, it's quite high. Omar, what's up, bro?
Why did you multiply by 2 for the p-value?
Ah, good question. It's a distribution thing. So strictly speaking, when I write phi of 3.25, underneath the hood, I'm actually meaning phi of minus 3.25.
Oh, okay, I see. Because there are 2 up there.
Yeah, and I only get that left side, and I got to double it.
Right.
Good question, though. Oh, that's a, I see. They did mean phi of 3.25, but it's fine. Again, symmetry.
Oh yeah, that's the same thing.
That gets you the same thing. Okay. If we want to, that gets us type 1 error, right? That gets us at what's our likely type 1 error. If we're thinking about type 2, we have to sort of specify if we mean one-sided or two-sided. For this instance, we specify two-sided. Same thing, right? But now, we're going to play a game from a previous class where we talked about how the probability of the mean, right, difference of means, is still a normal distribution. And so we're going to say, we're going to be a little bit algebraic, and we're going to say our new sample mean is some difference, some delta, away from our population mean. When we substitute that into our test statistic, it just simplifies really nicely, right? It becomes a normal distribution where instead of me being worried about what was my population mean, what's my mean, it's how different are they? That's it. And from that, that's a normal distribution, just the same as it always would be. And so we can calculate our two-sided error like so. Z alpha 2 minus the difference, the normalized difference, minus the alpha 2 minus the normalized difference. Still the same cumulative distribution function, but I'm just looking at how much I'm moving inside of Z alpha 2 space, given that value. It's a little bit weird, slightly. I don't know how accustomed you all are to transformations, unit transformations and stretching and so forth of graphs, but that's our Z value for this distribution. How much are we different from our original standard distribution? And so obviously for type 2 error, we just did the version that is the two-sided test. And we can ask how many samples would we need to reduce the two-sided error to a certain level of significance. And we can just do a fairly straightforward substitution. And it's a straightforward calculation. Only difference is it Z alpha over 2 for the two-sided or Z alpha for single-sided. I'll pause for a half a second. That was a little bit quick. Make sense? Derek, yeah.
I have mu minus mu naught.
Mm-hmm.
So the mu is just the, is it a measure?
Yeah, so it doesn't, the sign doesn't particularly matter because everything's symmetric, but the convention is mu is sample, mu naught's population.
I see, so it's analogous to x bar.
Huh?
So it's pretty much x bar. I never.
Gigapascal, right? That's your original unit. So 50 centimeters per second, 51.3. We're good? Christian? I'm sorry, ever so slightly louder, please.
Like the alpha and beta vectors, the values, those are the ones that you found like 2 hertz.
Yeah. So Z alpha, remember that alpha is your significance. Typically speaking, at the beginning, you fix it. You say, I want 0.05. Z beta is your type 2 error. Typically speaking, calculated. And so what these formulas are saying is, hey, I want a Z alpha 2 of this and a type 2 error of this, given my variance and how close they are to one another. How many samples do I have to take to get there? Or at least have confidence that I should have gotten there and thus can fail to reject the null hypothesis. Okay. So same problem as before. Sigma is 2, variance is 2, alpha is 0.05, n is 20, 5. How do we calculate beta, right? So delta equals 1 because we're assuming now our true burn rate's 49, previously it was 50. Z alpha over 2 because we want the 0.05 is 1.96. We calculate our Z beta as the square root of the samples divided by the variance. And we get the difference between these two cumulative distribution functions, right, which ends up being order of about 30%. And so we actually have relatively high type 2 error. You can go ahead and skip that. Okay. The main gist of this slide is sometimes we don't know the variance of our population, but we remember t-student distribution when we were looking at the table together. As the number of samples or the degrees of freedom increase, the t-student distribution very rapidly approaches the standard normal distribution. And so even if you don't know the variance, but you assume your population is normally distributed, once your number of samples gets to be relatively large, order of 40, then we can continue to use normal distribution even though we don't know the population variance. Right? That's the sum of that. I don't know the variance of my population, but I took 50 samples. Okay, well, I can continue to use normal distribution. Why is that? Oh, spitting my own words back at me. Because the t-distribution has a degrees of freedom, which is 1 minus the number of samples. And it's been demonstrated that as the number of samples tends to infinity, it goes to the normal distribution. Another way of saying it is, yes, I will still get outliers in a random sample of 50 samples, but they won't be large enough to continue to shift the distribution because I have enough samples down in the center of the meat of the distribution. If I do not know the variance of the population, we use the t-test. Right? So normal distribution, again, we have to assume that our population is normal. If we can assume that, but we don't know the variance, then, I mean, it's the same stupid equation as a normal distribution for our test statistic, except now we're going to use the sample variance rather than the population variance. We use that as an approximation. Yeah, Alex?
So you're technically using t-student for the test statistics,
Mhm.
but you're assuming that it's globally distributed because A is large.
Oh, we got different distributions. Thank you for that question. I'm hoping that was also Omar's question.
I was stretching actually.
Okay. So, we are using different distributions for the sample and the population. We have to assume that the population is normally distributed. So it can't be a uniform distribution, it can't be a chi-squared distribution, it needs to be normal. We use the t-student distribution in this case because when we sample randomly, sometimes we get really shitty measurements. We get an extreme outlier. For the normal distribution, what that's going to do is it's going to it way over. We can't use a normal distribution anymore because with a small number of samples, that outlier is going to shift my mean and possibly my variance substantially. The t-student has what's called heavy tails. So rather than following those exponentials down, it sort of spreads out and it can accommodate outliers. And so even though in our 5 samples, one of them is an outlier, I still don't move the population mean all that much. I can accommodate them. That's why. Is that clear? Yeah. It's the same as if you randomly sampled a student on their favorite professor, right? Who's your favorite professor? Mechanics professor, of course. But, right? You might get an extreme outlier. Someone might think Mrs. Strumus is a professor. Danny Bui, that's my favorite professor. Right? You can get extreme outliers. And so you want a distribution that accommodates those, and that's your t-student. Past that, right, other than the fact that we've shifted the distribution, so we either need a different table or we need to do some different integration, the rest of the problem is the same. Define your null hypothesis, right, equals that. What are your 2 alternative hypotheses? What's the probability it's below minus of that? Probability above, probability below. And yeah, you're using a slightly different distribution. If it's 2-sided, it's still alpha over 2, but now we've got degrees of freedom specified by the number of samples. Everything else is exactly the same. No difference. It's just realizing which one you're supposed to use given the situation. So we can think about an example, right? And we're making golf clubs. 15 drivers, right? We're interested in the coefficient of restitution, means how quickly it snaps back. We want to know within some confidence that the mean exceeds 0.82. We have a set of measurements. We can calculate a sample mean, and PowerPoint can just keep dropping. It's fine, I don't mind at all. We don't know the variance of the population, so we have to calculate it ourselves, and we know we're in T-student world, but we can calculate it. And we want to know that if it exceeds 0.82, ergo it's a one-sided. And now we set up our hypothesis test, right? And we do so in a systematic fashion. What's our parameter of interest? Mean coefficient of restitution. What's our null hypothesis? That it's 0.82. Our alternative hypothesis is no, it's bigger. It's better than that. Or worse, I don't know. What's better for golf club? Should it be lower or higher?
Depends on the player.
Depends on the player. Someone as inept as myself.
Then it should be less stiff.
It should be less stiff. Oh, interesting. Again, we didn't know the variance, and so we're going to need to use the t statistic, where we're looking at the difference between our measured mean and the population mean, standardized by our sample variance and the number of observations. We reject p0 if the p-value is less than 0.05, right? Because that's our fixed significance. We know x bar, we know the variance of the sample, we know the mean, we know the number of samples, we can calculate t0. Bippity boppity boop. All right. Now we got to look at a table. So for the normal distribution, like back of your head, 1.96, 0.05, 1.96 for two-sided. For this one, I'd have to look. We got 14 degrees of freedom. T0, 2.72 falls between two values, 0.01 and 0.005. Doesn't matter. So if I were looking at a table, I can't get the exact value. But does it, oh god damn it. It's all up there. I need to move to having the text come up bit by bit. Anyway, right, it's between 0.01 and a number less than that, we win. We can successfully reject the null hypothesis. It is greater than that. Cool. Cool. Type 2 error is basically the same game that we would have played with the normal distribution, only we use the t-test statistic. This is where life sucks if you're just using a book. There are separate tables for every freaking degree of freedom and every significance level. And they're not even tables, they're graphs. It sucks. It is so much better to be able to do this with a calculator or with a computer. But they have these things. They have to then introduce this D, which is just the difference between these two divided by sigma. It's terrible. They have separate graphs for one-sided and two-sided. It's a mess. One-sided less than, one-sided greater than, two-sided. They have plots. If you want, in class, I'm very happy to show you how to use them. But I don't think it was a useful thing to be able to do for like my grandparents. for my grandparents, which would be like what, your great-great-great-great-grandparents? Let's jump that. We're right up on time and we'll switch to the next topic after this. But last thing is remembering that when we sample, our sample variance is not an estimate of the population variance. If we want to know the population variance, we need to use chi-squared. How'd you like the diffraction problem? How'd you like minimizing chi-squared for that bad boy?
It's been a while.
It's been a while. We've completely forgotten it, either through alcohol or tears, but I'll take both. The only difference is if we don't know the population variance and we want to, we use chi-squared distribution. Our null hypothesis is the same as it's ever going to be, that it equals some value. Our test statistic is the chi-squared statistic, which is degrees of freedom times the sample variance divided by sigma naught squared, which is our null hypothesis. We're not going to use that value, right, just the same as we didn't use mu0 previously, but that's our test statistic. And our alternative hypotheses are, rinse and repeat, right? It's the same as it would have been for normal, same as it is for t-student. The only thing is we lose frequent symmetry because that is an ugly-ass distribution. And so we can no longer, for the two-sided, just take this and double it. We have to do the integral from there to there and then subtract it from 1. No choice. Or think of other creative ways to do that. All right, so that is 4 o'clock. I have a proposition. Let's do a real quick, like 5-minute break, come back at 4:05. Let's see if we can finish a little bit early, because I have to go and pick up my wife because we're going to something downtown